Hello and welcome to this workshop session, Unlock Value and Gain Deep Insights from Your Data with SAP HANA Cloud. My name is Markus Fath, and with me are my colleagues from Product Management, that is Rüdiger, Karl and Christoph Morgen. We also have Matthias Menz from Solution Management and Matthias Kemeter, who is the Development Manager. My colleagues will be monitoring the questions in the chat. So nice title, Unlock Value and Gain Deep Insights. What we're actually going to do is to show you some of the capabilities of HANA's smart multi-model features that comprises spatial, graph, predictive analysis. And we also will cover a little bit of enterprise search and give you a glimpse on the JSON document store. This is a workshop, however, I will walk you through the exercises. Maybe I will also run now and then, but the thing is, the data as well as the code. So everything that I'm going to show you is available on that GitHub repository that you see the link here. So if you feel like you would actually touch the code on your own, feel free to get there, get the data and the code, sit down on a Friday afternoon and really repeat the exercises and go through them step by step. The session, of course, will be recorded and will be available afterwards, so you can refer to it as afterwards anytime. Please be advised that large parts of the workshop exercises, they will actually run on an SAP HANA Cloud trial instance. However, two of these exercises require the so-called script server and the document store, and those are components or services which we need to be enabled on an SAP HANA Cloud system. Now, this is the repository on GitHub for this workshop session. It's called DAT262. Here's what we're going to do. We will mainly work with data from the automatic identification system, for short AIS, which are basically observations in space and time. In specific, we will work with AIS vessel data. So these are signals from ships that are recorded by a US government agency. We have downloaded the data and we're using these space-time observations in order to show some spatial and graph and predictive capabilities. So we will start off mainly working in SQL, showing you some processing patterns and analysis queries in the area of spatial data. We will later then also use some graph capabilities in order to calculate routes. We will use a time series forecast algorithm from the so-called PAL library, predictive analysis library, in order to do some time series forecasting. Then we will leverage the enterprise search stack to search for some vessels that we have in our data. And towards the end, when we're going to touch the JSON document store capabilities in HANA, we will switching the scenario a little bit, and we will be working with the global entity graph from the GDALT project. And GDALT is a project that monitors news articles worldwide and does some pre-processing, does some analysis on that. And the global entity graph gives us access to things like persons, organizations, locations, events that are mentioned in these news articles. And we will use the JSON document store to ingest and process the data. With regards to the individual exercise step, there is really a lot that we are going to cover. We will start off with a little bit of data preparation, so ingesting AIS data, automatic identification system. Then we will check for certain vessels within national park boundaries where they maybe are not allowed to travel actually. Then we will run some queries to understand vessel motion characteristics. Essentially, we will be deriving speed and acceleration from the individual geolocation observations. Then I'll show you a glimpse on spatial clustering, so how to get an idea on density and distribution of the observations. We will then use the graph engine to calculate routes on a lake. Then we will extend the idea of spatial clustering and add a third dimension, which is a time dimension, in order to organize the data as such that we can run time series forecast algorithms in order to understand what potentially traffic, so essentially the number of ships in a certain area, might be in the future. And again, towards the end, we're looking at search capabilities in the search UI that is part of SAP HANA Cloud, and we will give you a glimpse on the document store and graph. I know this is really a lot of code to cover, and I'm pretty sure one or the other might not understand each and every detail of what I'm going to show. But the idea also is to kind of give you some ideas on what could be done with space and time observations, and give you, for certain patterns, really functions that you can easily adapt to your data, essentially reuse. So you're always welcome to get back to that GitHub repository where all the data and code is found. Okay. There is a little bit of additional scenario description here also on GitHub. It's a little more information in how to set up your HANA system with regards to authorizations if you want to run the session. And with regards to tooling, I will be most of the time using dbeaver, which is an open source database administration and development tool. I will be using the SQL console there. And in addition to that, I will also be using QGIS, which is an open source GIS client, a geographical information system, in order to put our data and analysis on a map. I will also briefly touch HANA-ML, which is the Python machine learning client for SAP HANA. And I will also use Cytoscape in the end, which is a well-known graph analysis, network analysis, rich client. With regards to, let's say, the architecture, everything that we run with regards to logic is run inside of the SAP HANA database. So we will be using its spatial capabilities, its graph capabilities. We will be using an algorithm of the PAL, the predictive analysis library. So all that is part of SAP HANA Cloud. In order to interact with the SAP HANA database, as I said, I will most of the time use dbeaver and its SQL console, but we will also using Database Explorer, which is the development and monitoring tool for SAP HANA Cloud. As I mentioned, QGIS will be sitting on top. That will be visualizing data. We'll be using enterprise search user interface. And we will also be using Cytoscape. Jupyter Notebooks will be used in order to ingest some JSON data into the HANA document store. So this is the kind of the tooling that we use. Also, you will find some of the additional materials here mentioned. It's large links list on resources for spatial graph and machine learning topics. So with that, we are all set. Let's start with the first exercise. And in the first exercise, we will load the data and prepare the data. As a matter of fact, in my demo system, I already did that. So I will just talk you through. The data that we are going to use in this workshop, in this demo, is located in this data and script folder. Let me open up that data and script folder. You will find these container files down here. Here are 2 data files with our raw AIS data and 2 additional packages which we will use throughout the workshop. This complete script, so everything that I'm going to show you, is also part of this folder. The first thing that you need to do if you want to run the exercises on your own, you need to import the data. So you go to HANA Database Explorer, you right-click the catalog, and then you say import catalog object. And then you point it to the data files, which I just showed you, and upload the data. And the data is then uploaded into a table. We need to do that 2 times because there are 2 files to be imported. We had to split the files into 2 because of file size restrictions on GitHub. What I already done in the background is I merged the 2 tables, which we just imported, into one so that I have all in one place. So we have around 8 million AIS observations in our single table here. The next thing that I did is I generated geometries. What you see in the raw data, there is latitude and longitude GPS, kind of GPS coordinates for the ships. It's the vessel's positions. However, in the raw data, it is provided as 2 double columns, latitude and longitude, as you see here. In HANA, we convert them into real geometries in our native geometry data type. And for that, you need to create 2 spatial reference systems in the HANA database. So what is a spatial reference system? So geometries are usually defined taking a specific model of the Earth into account. There are round Earth models, and there are kind of projections to that. So everything that you view on a flat screen kind of is a projection into a flat surface. There are global spatial reference systems, for example, the one used by the GPS system. And there are local ones, which are more accurate because they model the Earth, the actual surface of the Earth, for a specific area in much more detail. And this is why we are creating 2 spatial reference systems here. If you need more background, just refer to the spatial documentation. There's a lot of written to that. What we do, we alter our table, we add an additional column that will contain these geometries, and we generate these geometries from our longitude and latitude double values. Then the final step we need to do before we actually going to start with the workshop exercises is we had to remove some duplicates. So that means there were duplicate observations for the same vessel with the same timestamp. And that kind of is not very helpful for our analysis. So we just removed the duplicates. So these are the steps that are already made in the background. I'm switching now over to dbeaver, to the SQL console, and start with the actual workshop exercises. First of all, let's take a look at the data that we have in the system. This is part of our AIS data table. You see that there is a column MMSI, which you can think of as the kind of the vessel identifier. Actually, it's the identifier of the AIS asset, that thing that sends out the sensor readings. We have a timestamp, and now we have that shape column. So this is actually a geometry that we can plot on a map. So we see here a couple of observations from a single vessel at certain timestamp, and that vessel was traveling here, which is an area around Lake Michigan. Now let's see, the data that we have is around 8 million observations, and they are from May and June 2017. Let's take a look at the number of vessels that we have in our data table. There are approximately 800 vessels from which we have AIS observations in that area, Lake Michigan, from that time, May, June 2017. If we do a basic aggregation and understand that for how many observations are there for a single vessel, again, MMSI can be thought of as the vessel identifier. So for this vessel, with that idea, there are over 75,000 AIS observations, AIS records in our data. And if we break that down to the actual dates, we see that there are roughly over 1,000 AIS observations per day per vessel. So this concludes the kind of the data preparation. Now let's start with the fun stuff. The first thing that we are going to do is we will identify vessels within national park boundaries. In Lake Michigan, there is the Sleeping Bear Dunes National Lakeshore Park. You see here the boundaries of this park. And the first thing that we want to do is understand which vessels have crossed the boundaries of this national park, because it's actually an underwater preserve. So I'll switch over to the Beaver again. I will launch my script and I will bring up the boundaries. So it's actually a single geometry that represents these areas in Lake Michigan. The first thing that we want to do is use a very basic spatial predicate. It's called ST within, which basically checks if a point geometry, so our AIS observation, is within a polygon. So let's run this query in order to understand, are there observations, are there ships that have crossed the national park boundaries? And as a matter of fact, there are around 500 observations from 4 distinct ships. Now, we want to understand which vessels and when they have crossed the national park boundaries. So now this query does the following. It selects those AIS observations, again with the ST within predicate, so spatial predicate. And what we are doing then is we will use a so-called window function. We will take all the observations, bring them in an order according to their timestamp, and then we will make a line. We will draw a line from an observation to the last observation. So we kind of get a route of the ships that crossed the national park boundaries. So these individual lines that we are going to make are actually then aggregated by that stCollect aggregation function here and brought into a single geometry. So let me run that query and let us understand what these ships are doing. This is the result. We see 4 vessels have crossed the national park boundaries. There is that one vessel called Lauren A, and we can take a look at the observations here. So here are the individual AIS observations that crossed the national park boundaries. And this would essentially now be the route. So remember, we took the observations ordered by timestamp, and now we simply created lines between each individual point. So that gives us an understanding what that vessel did. It entered the boundaries and then it kind of headed back again, so to say. In order to be able to visualize that in QGIS, our open source GIS client, we will create a table out of it. And I will show you now QGIS. It's connected to my SAP HANA system, and it pulls data from our tables. What we see here are the raw AIS observations, those 8 million data points. And obviously, these 8 million data points simply plotted on a map doesn't tell us anything. But we've started to analyze the data and understood which vessels cross the park boundaries. So this is how you can plot the individual AIS observations on a map. And the color indicates different vessels. So now here we see the structure that we've just been examining. So that basically concludes our first exercise. We have seen a polygon or multi-polygon describing our national park boundaries. We've used the ST within predicate in order to check which vessels, which AIS observations are within the national park boundaries. We have used a simple ST make line in order to create a line between two consecutive AIS observations. And we collected the geometries into a single geometry and then plotted that on a map. Now let's shift gears a little bit. And the next thing that we want to do is understand vessel motion. So we just have individual AIS observations. What we want to understand in this exercise is actually the speed of these vessels and the acceleration of these vessels at each individual point. We want to understand the actual route. We're constructing the trajectories. And in the end, we will identify 12 or stop locations. We want to understand points within a route where a vessel stops, for example, at a harbor. So let's jump into this exercise. What we are going to do is we are creating a kind of a stacked query, so to say, in order to explain you the actual logic, the processing step, how we derive speed and acceleration from the individual points. I've splitted the processing logic into 3 steps. The first step, we will be calculating delta S and delta T. So for each pair of consecutive points, we will be deriving the spatial distance and the temporal distance, so the seconds between the AIS observations. This is the first thing that we are going to do. And I've wrapped that in a SQL view, which we are going to do. So what you see here, again, we make use of these window functions that I already touched. So in this line, you see that we're using that window function in order to partition our AIS observations by the individual vessels and then order them by timestamp. So this is that partition by MMSI and order by timestamp clause. And once we have that window, we can use the lag function, which is encoded here, in order for each record to access its previous record. Now, once we have for each record its previous record, we can calculate the spatial distance between the 2 points and the temporal distance. This is basically what happens in that first view. We're calculating delta S and delta T. Let's see the result of the query for partial data. So now for this vessel we selected, we do have a set of consecutive points. And for each pair of points, we understand the spatial distance in meters. So there are roughly 250 meters of distance between these 2 points up here. And there is a roughly 60-second interval between these AIS observations. So this is our first processing step, calculating delta S for spatial and delta T for temporal. The next thing that we will do is we will put a view on top of that view. And now we will basically or mainly derive the speed by simply dividing delta S by delta T. So let me create that view. And let's take a look at our process results after this second step. So again, we are for this vessel, for this observation, we do have calculated the speed in meter per second. So we roughly see that this vessel at that point in time is driving with a speed of roughly 4 meters per second. In addition, we're simply summing up the total distance that this vessel has traveled up until this timestamp, and we are summing up the total timestamp. So our vessel up until that point has been traveling for 270 seconds, and it has gone roughly a kilometer. So the last thing that we are going to do is we create another view where we simply calculate the difference in speed and divide it by time, again using that window function. And of course, this gives us the acceleration. So this is the last step in our motion statistics calculation. What we've seen is we have the speed, we have the change in speed over time, and from the change in speed over time, we can calculate the acceleration. So let's take a look at if this makes sense. I'll highlight a couple of points. So this is essentially making up the trajectory. So there is a vessel that approached that harbor over here, and we see for sure it's decelerating. So the speed actually decreases while it's approaching the harbor. Now, these are the three basic calculation steps that we make in order to calculate motion statistics. What I've done for convenience reasons is I've put the very same three processing steps into a single user-defined function. So I can reuse it and call it in a single statement. Another reason why I've created that function is because there is an easy way to handle a filter condition. And I want to use that motion statistics calculation function, for example, to be run on all the AIS observations within a week, or just for a single vessel or for a vessel type. And the way to do that is by handing in a filter condition, a kind of a SQL-like filter condition, and then use the apply filter function within that code block here. So my data is filtered, which is in that table. And then basically the three processing steps that I just explained are run just in a single statement. So let me create that function. And here is how you would call it. Our function is called fMotionStatistics. And as I said, it simply takes a kind of a SQL where clause as a filter condition. And for example, here, I'm looking at a single vessel and a roughly 1 day interval for which I would like to calculate the motion statistics. So I'm calling that function, and now I have the motion statistics for this vessel, starting at that specific day at 10 o'clock. There are now these motion statistics, and I can understand that, again, once that vessel is approaching the harbor, I can understand its speed and its acceleration. Now, the other thing that we can do with these motion statistics, and I will jump over to Database Explorer. We can use the native charting capabilities on top of. First, I'll persist the data in a table. We will run the SQL query. Essentially, we would use the analysis, the built-in analysis capabilities of Database Explorer. So I'm running on my motion statistics table, which I just created. You can pull simple pivot charts here together. So what we see here, the blue line is actually the speed of my specific vessel. So you see here a time interval where the vessel was going with roughly 15 meters per second. And the orange line is then the distance that vessel traveled. And obviously there have been 2 time intervals where that vessel was really traveling with a higher speed, where you consequently also see that the distance has increased that this vessel was going. So this is also an option on how to leverage the motion statistics. The next thing that we are going to do is to calculate vessel trajectories. Remember the first exercise where we simply made some lines between 2 subsequent AIS observations, 2 points. Now I will create an actual line string that is made up out of multiple points, and where we actually also have a so-called M value, which is usually a kind of a timestamp. So we actually see the temporal aspect of that trajectory. And as of today, the most convenient way to create a line string out of multiple points is actually to use a string aggregation function where we simply concatenate the x and the y coordinate of our geolocation, aggregate it into so-called well-known text format, and then create a line string from that. So what that does is basically creating a single geometry, creating a single line string representing the trajectory of this specific vessel that we just see here. Obviously, it's a ferry vessel that's going back and forth between these two islands. If we take a look at other trajectories, we see that this vessel is going up here on the east side of the lake. Maybe see if there's anything else here. This vessel really, maybe it's a fishing vessel or it's just a pleasure craft that's going back and forth. So this is a single line string, which is created using that string aggregation function. Again, might not be very nice, but it's the most convenient way to generate a single line string currently. Now what we can do with that is we can generate the trajectories for cargo ships and passenger ships specifically. The AIS data that I have also has some information on the vessel types. So the vessel type 1004, these are the cargo vessels. And the vessel type 1012, these are passenger vessels. And in order to analyze the different trajectory patterns of these vessel types, I will simply create a table that will contain my vessel trajectories for the cargo ships. I'll now run the very same query, restrict it to cargo ships, and put it in this table. And I'll create another table and put in passenger trajectories from a time interval of 7 days. Now let's again switch over to QGIS in order to understand these trajectories. Let's first bring up, okay, this is one thing I forgot. Shortly back to the motion statistics, what we generated earlier. So this would, for example, be a mapping of the motion statistics in a 3-hour interval. And what we do see all the ships encoded by their speed. So red means it's a vessel going with high speed, which we derive from our motion statistic logic, and blue means it's a vessel going with low speed. But actually, what I wanted to show you is, first of all, the trajectories of cargo ships within a 7 days interval. So we see here different colors indicate different vessels. So we mainly see trajectories, so vessels, cargo vessels going up from south to north or north to south on Lake Michigan. If we're looking at the trajectories of passenger ships, we mainly see 2 ferries standing out here, which go from west to east. Again, single color indicates a single vessel. So there is a ferry going east to west, and there is a nice area up there. There are a lot of ferries are going between these islands. So it's essentially a trajectory which represents that ferry vessel going back and forth. So now this also kind of motivates the next step that we want to make, and that is understanding stop locations. So where does the vessel actually is in motion, and where does it stop, for example, to load off passengers and the like. And this will be the next step of analysis. We will calculate stop locations or dwell locations. And the logic behind will be, we will be looking at a time interval, let's say 5 minutes, and we will calculate the cumulative distance that a vessel goes within that 5-minute interval. And if the cumulative distance is below a certain threshold, let's say 100 meters, we say, okay, this vessel is most probably not in motion. Whereas when we see 5-minute interval where the vessel cumulative distance is below above 100 meters, we say, okay, this vessel is traveling. Now let's see how we can implement that logic, that stop location find logic. And again, like before, I have split the actual processing logic into 5 steps. And the first step is we will be creating sliding windows. So essentially what we will be doing is we will join our AIS data to itself. And the join condition will be, okay, for each record, we will be joining the records from the same table, which are within that 5-minute interval. And that means 5 times 60 seconds here. This is our join condition. So there's a little bit additional logic in that view, but basically this is what it does. It creates sliding windows. Now let's take a look at a specific example. Let's pick, for example, this time interval here. So at 15:35, there is an observation of that vessel. And what we did is we joined the previous 5 minutes interval to that observation. And now again, using window functions, we can calculate the distances between the observations within that window. And as the next step, we will simply summing up these distances and check if they are above a certain threshold in order to understand if this vessel is in motion or not. So step 2, summing up the distances. So we essentially will be summing up these distances and say, okay, if the distances are above 100, below 100 meters, we say no motion. Otherwise, we say motion. So let's create that view and see what the output of that processing step is. Now we see this vessel, again with a timestamp. We see that vessel is going somewhere on Lake Michigan. Here we see the cumulative distance. We see within a 5-minute interval, it nearly goes 2 kilometers. So as this is above our threshold, we say this vessel is in motion. We set that motion marker. Let's scroll down a little bit and understand that area around here. Here, obviously, that ship is kind of approaching that harbor. So we see within a 5-minute interval, now the cumulative distance drops below 100 meters, and we simply assign a no motion flag. So this is the second processing logic that we are doing here. Let's go ahead. Obviously, interesting are these changes in motion. So when we say a vessel is stopping, so we simply observe this motion marker. And again, using a window function, comparing the motion marker to the previous one. And when we say it's going from motion to no motion, we say kind of set a motion change marker to stopped. So let me wrap this additional processing logic in a view, and let's observe the result of this processing step. This is nothing new. The vessel starts in motion. Further down here, it switches to no motion. And that is where we assign a motion change marker, indicating this motion, this vessel has now stopped. Now, the next thing that we are going to do is we will use a window function again and simply counting these motion change markers, which gives us a number which indicates the trip segments. So we're saying, okay, there's a first segment where this vessel is in motion. This is segment 0. Then there is the next segment within that trip where the vessel has stopped. It's not in motion. We will assign a new trip segment to that. So again, let me simply execute that view with that one specific window function. And let's say that this trip segment is being generated by simply counting the motion change markers. So obviously there is a first trip segment where that vessel is in motion. So trip segment is 0. Now it has stopped, and we see a new trip segment is actually generated. Now we have that trip segments at hand. We can actually aggregate the our data along these trip segments, and that is the last step that we are going to do. We will be simply calculating the minimum of the timestamp within that segment. So this is where the segment starts, maximum of the time segment, which is the segment end, and do some additional aggregations here. So the fifth piece of logic, and this is how the result looks like. Now we have, for this vessel and that timestamp, we have 3 segments. The first segment starts at 1533, where the vessel is in motion. So this is the trajectory here. Then there is a no motion segment. So basically overnight, this vessel basically was lingering around in this harbor. And then again, a motion segment started where the vessel the next day started on its trip to the south. So this is our 12 location and trip segment logic. We cutting the individual AIS observations into individual trip segments, indicating where motion or no motion is. As above, simply for convenience reason, wrapping that complete logic in a single function. Now giving me also control over my definition of what does no motion mean. You simply say, okay, that function takes in a time interval, where I can say, okay, within 5 minutes, not more than 100 meters. This would be my no motion condition. And these are parameters of this function. Again, that function may seem a little long, but it's abstract enough for you to be reused if you're looking for the same piece of logic. So I've just generated that function, and here's how we call it. Again, we hand in a filter condition. For example, we want to understand trip segments and dwell location for that specific vessel. And now our parameters here are for stop conditions are within an 8-minute interval, not more than 80 meters of movement. So if I run that query, that function, I see that this vessel over its complete time interval, which is 2 months, something like that, does have areas or does have segments where it was in motion. We do have the start and end time of that segment, and we have certain segments where that vessel did not move, essentially according to our definition. Now, in order to visualize that again, I will simply create a table which contains the data, so I can leverage it again in QGIS. So here we're pulling the data from the table that we have just generated. And now we see the trip segments of a single vessel within 2 months of observation. The individual colors now indicate individual trip segments. So motion segments between 2 stop locations. You can take a closer look. It's the very same data, but now we can zoom in here and see a different color coding. So the blue lines will obviously indicate points in time where the vessel was in motion. And here are the segments where the vessel did not move. And as you can see, it's sometimes not too easy to really separate the segments where motion is versus no motion is. Obviously here the ship wasn't moving that much, but here it was moving a little bit in between. So it was making some meters within some seconds, but it was below our threshold of what we said should characterize motion. So I know this was a lot of SQL code. It was the longest exercise. So bear with me now as we quickly recap what we did. We started with some logic where we could derive speed and acceleration from the individual observations. We made use of window functions, calculating spatial and temporal distance between consecutive points. In the end, we wrapped that processing logic into a single function, being able to also hand in a filter condition as a SQL where clause. We've taken a look at the motion statistics. The next thing that we did is we generated vessel trajectories. So essentially a single line string made out of multiple points in our observation. And this was kind of the result, the single geometry representing here how the ferry goes back and forth. The last thing that we did is the calculated 12 locations or stop locations. And for that, we had a 5-step logic. We started with a sliding window looking at n minutes or 5 minutes interval of observations. We calculated distances and set a threshold, a motion marker, so to say, if the distance is below a threshold. When we looked at motion change, and based on that motion change, we generated that trip segments numbers, and then we simply aggregated the complete route by the segments. And this is what we ended up with, a single table function, again, ready to be reused and easily adaptable to your own data. Now, to the next exercise. Here we will be looking at spatial clustering. We want to understand the density, the distribution of observations on Lake Michigan. And for that, there is a built-in syntax to run spatial clustering. And that syntax in SAP HANA is group cluster by. So what does spatial clustering do? It essentially generates a grid over your area where the observations are. So think of rectangular grids, or in our case, hexagon grids. And it's summing up the data per individual grid cell. So that's what spatial clustering does. Let's go over to the code and see that in action. Here's our statement. So we will be using our AIS observations. We will use that group cluster bias syntax, which does spatial clustering. And we say we want hexagon cells for the clustering to happen. And I want 400 hexagon cells in Y direction. So that makes up my spatial grid. And within that grid cells, I want to count the observations and I want to count the individual ships. So let us run that for our 8 million AIS observations. What this query returns is basically a set of cells which are represented by a hexagon polygon. Now here we are in the area of the Chicago port. And we see in the 2 months of our data, within that area, hexagon area, we have roughly 300,000 AIS observations coming from over 100 ships. So this is a result of the spatial clustering. Again, like before, we will store the result in a table in order to visualize it in QGIS. So first of all, we will be aggregating all AIS observations along that spatial grid. And then we want to understand different density, different distribution in observations between cargo ships and passenger ships. So I'm doing the very same. I'm creating a cargo table, and I'm restricting my spatial clustering to the vessel type 1004, which indicates cargo ships. And I will do the very same for passenger ships. Separate table for passenger ships and aggregating via spatial clustering. Now I can consume my data in QGIS. So now, first of all, let's understand the spatial density on Lake Michigan in that 2-month interval. So what we see here is red areas indicate a high number of observations, and blue areas indicate low number of observations. These are for all the vessel types on Lake Michigan. Now I can bring up the data for cargo ships only. And of course, the density, the distribution of cargo ship observation looks a little bit different. Again, we see that north-south kind of common routes. And again, for passenger ships, we see the spatial distribution along hexagon grid cells. Again, that ferry going back and forth here. So what we did is we introduced spatial clustering. Besides hexagon, there are different types of spatial clustering methods also available, for example, for rectangular grids. We simply generated a table and filled it with the results of spatial clustering. And we understand, let's say, density and distribution for cargo ships and for passenger ships, respectively. Now, the next thing that we want to do is do a little bit of routing for our vessels. And up until now, we have used plain SQL in conjunction with spatial data. Now we will be using the HANA Graph Engine. And the HANA Graph Engine operates on network-like data. So data that is made out of vertices and edges. You can think of it as a street network where you have road segments and road junctions making up your graph, making up your network. Now, if we want to do some routing for our vessels, we don't have a street network on Lake Michigan. So what we want to do is essentially create something like a network on Lake Michigan, which allows us to find suitable routes for cargo vessels. And the network that we are going to generate will be based on spatial clustering results. What we want to do is understand common routes of cargo ships and kind of have a specific cost function on that network that allows us to calculate routes that are not only short in terms of length, but which are appropriate because they kind of align to common cargo ship routes. So this is our task right now. And for that, we will first be generating a network. A network is made out of vertices or nodes and edges in between. And the first thing that we want to do is create the vertices of our network. I generate a table, and I will simply use spatial clustering to generate the vertices of my network. So again, what you see here, the group cluster by shape kind of syntax. And I will use spatial clustering to generate data and fill it into my vertices table. So what that basically gives me is a table which basically consists out of hexagons. I can visualize that in QGIS again. And what we see is nothing more essentially than these hexagons. This is a tessellation of the surface on which we want to find routes. So these are the nodes in our network. So what is still missing is that we need to generate edges so that we can actually do some routing. And this is what we are going to do next. As we want to find routes for cargo vessels in specific, we introduce that cargo transit cost factor. It's nothing that you can really explain, but we will say wherever on Lake Michigan there are areas that cargo ship usually travel as a common route, we will put a lower cost on these edges. That will lead that our shortest path function or our least cost pathfinding function later on, will try to find routes that stick to commonly used cargo routes. And for that, we are introducing that cargo transit factor. And we simply set it according to the number of cargo ships that we observe in that specific area. So it's just a piece of code that sets a cargo transit cost factor. Again, a cost factor of 1 means cargo ships don't usually go through that edge or through that node. And the cost factor below 1 means cargo ships usually travel through that area. So now we have a first part of our network on which we want to route. For the edges, it's currently a little bit tricky. We need that specific view, which essentially for each hexagon calculates its neighbors. There are 6 neighbors, and with that hexagon grid, we can identify these neighbors. Made up that view, it simply gives me back a set of neighbors. Now that I have a set of neighbors, I can construct my edges. Bear with me for a second. I will create an edges table, and I will now use that neighbors view, which for each hexagon gives me the neighboring cells. And I will, for example, calculate an average cargo transit cost factor. So I have a weight, a cost assigned to the edge over which I want to do routing later on. Let me generate the data and take a look at what we did. This is the data that we just generated. So it's simply a set of edges between the nodes we had at first. So on these edges, now we can find routes. Red color indicates there are a lot of cargo ships usually going down that edge. Blue means there is an edge, you can travel there, it's safe. Ships have been there, but not usually cargo ships. So what we want to do next is essentially use that network in order to find a route from Menominee up here down to Chicago. And for that, we're using HANA's built-in graph engine. Let's switch over. What we need to do in order to utilize the graph engine on top of our data, we need to create a so-called graph workspace. And the graph workspace, think of it as a kind of a view that tells the system where are my vertices and where are my edges. So we create that graph workspace, and we simply point it to our edges table and now to our vertices table. That's the only thing that we need to do. Now the graph engine is able to see that graph and operate on the data that we just generated. For the path calculation, the least cost path calculation, we're using a function. However, that function is not written in SQL or SQL script. It's created in GraphScript or Graph. It's a domain-specific language. It's a proprietary language for our graph engine. And basically what that function does, we give them the graph, a graph workspace, which we just generated. We hand in a start and an end vertex that will be Menominee up in the north and Chicago in the south. And then we will calculate the shortest path with a custom cost function. And now this is a little bit of the secret sauce here. We're not simply summing up the length, so we are not calculating shortest path in terms of distance, but we will be trying to balance between the shortness of the path and we're finding a route where cargo ships usually go. So we are taking that cargo transit cost factor into account. So this is a custom cost function that you can throw to the HANA graph engine and utilize in order to find the least cost paths. So let me generate that GraphScript function. It takes a start vertex. This is the vertex for Menominee, an end vertex. This is for Chicago. And what it does, it calculates a route. So let's visualize that route. I will do that by simply wrapping my shortest path function that utilizes the graph engine, takes a start and an end vertex and some weight factor on that cargo thingy, and I will wrap it in a view. And from here, I can consume it in QGIS. Now, this is the route I found. So obviously, if we are going from up here, Menominee, we're taking the canal here at Sturgeon Bay, which is here, in order to go down to Chicago. Know that this is not the shortest path. It's a path that actually tries to stick to commonly used cargo routes where it makes sense. So this is a result of our custom cost function, essentially, that the route tries to align a little bit with common routes. Now, let's get into Suez Canal blockage scenario. Let's say I've planned this route for my cargo ship, but now the guys at Sturgeon Bay tell me they need to maintain the bridge and the canal is not free for cargo ship traffic. So there is a blockage at Sturgeon Bay. So I need to calculate an alternative route. We will simply simulate a blockage by setting an attribute in our underlying network. So we're saying there is an area, there's a set of edges in our network which is blocked. We can't go there. Now, custom cost function takes that into account. So we will simply set a blocker, go back to QGIS, hit F5, and what we see now, because of Sturgeon Bay is blocked, an alternative route is found to Chicago, which goes up here. Now, obviously, that route looks a little bit longer compared to the original planned one. And the question that we have as a cargo ship captain is, we will arrive at Chicago probably a couple of hours late. What does that mean for my unload schedule? So the next thing that we want to do is we want to forecast the traffic at Chicago for our new estimated time of arrival in order to understand if there is potentially a traffic jam, if there is potential high traffic, and I need to prepare myself for longer wait time at Chicago port because there are vessels in front of me. This will be the next task. Let me take a second in order to see if there are some questions up to now. No, I think that looks fine. So what we are going to do is we will head up and beef up our spatial clustering so that there is a time dimension that we can use in order to leverage a time series forecast algorithm. So again, we have an alternative route. We need to deviate. We want to understand the predicted traffic down here at Chicago. And this is why we are getting into spatiotemporal clustering. Let me create structure that we are going to use. It's going to be a space-time cube. Think of this data structure that we are going to create now in the next exercise. We still have X and Y dimension, which is basically the spatial location of our AIS observation. So this is spatial clustering. It's a single time slice here. We're adding now the temporal dimension as a set dimension. So we are calculating actually multiple time slices for each time interval we are requesting and running spatial clustering for each time slice. So we end up with that kind of cube structure. So for each and every cluster cell, so these have been our hexagons, now we have a series, a time series of AIS observations. And this time series, or the set of time series, This is the data on which we do time series forecasting in order to understand future traffic. So keep that cube kind of structure in mind, although we will be operating on hexagon cells and not rectangular grids. Spatiotemporal clustering. So the first thing I will do is I will create a function which does spatial clustering for a single time slice. So hexagon clustering for time slice, it is called. What it takes a start and an end timestamp. This is a time interval for which it will collect the data from our data table. So here's the filter condition, start and end timestamp, and it will run spatial clustering, which we already know, based on given boundaries. So we will keep the spatial grid constant for all the time slices. This function calculates spatial clusters for an individual time slice. Of course, that function is not enough. We need an orchestrating function that generates the time intervals and calls that function that we've just created. And here, let's do a quick sidestep on how we generate the time series intervals. For that, we are using a built-in HANA function called series generate timestamp. And what it does, it takes an interval definition and a start and an end timestamp. And what it generates out of nothing, basically, is that type of information. So it says, okay, I am using 8-hour intervals starting at that specific timestamp, and I'm generating a couple of bins or time series intervals. And this is the logic we are going to use in order to define the set dimension, so the temporal dimension in our space-time cube. Now, over to our orchestrating function. We call that our function create space-time cube because that is essentially what it will do. It's a single function that basically it takes a time interval definition as an input. What it does, it first of all calculates the spatial extent of my complete data. So what's the grid then to be aligned to? Then it calculates hexagon clustering like we did before on the complete set of data so that we have a stable grid which we can use in all the time slices. Then we are deriving the minimum and the maximum timestamp. So this is the maximum interval in our data. And we're taking the maximum and minimum interval of our data and generate a time intervals from that based on the interval that we give the function. And we will choose 4-hour interval in order to divide our time slices. The next thing is the map merge operator in SQL script. If you don't know it so far, I'm using it over and over again. Basically what it does, you give the map merge operator function, which is our spatial clustering per time slice, and you give it a set of data. And what it will do is, based on that set of data, it will call the one function multiple times in parallel, and it will simply merge the results back. So as we're doing the very same operation for each time slice, we're using the map merge function to parallelize these time slice clustering function calls and getting back individual results and merging them into a single table. That is what map merge does. And then finally, we are simply projecting out the results. It's a little bit of null handling. So let me generate that orchestrating function, which calls the spatial clustering function per time slice. What we do is we simply generate a table from that orchestrating function where we say, okay, I want 50 hexagons in X direction, I think that is, and I want the time slices to have 4 hours intervals. So I can generate that table from here. Now it will roll up 8 million observations into that 3-dimensional space-time cube. And this should be done by now. And we can look at a very specific time series now. We are looking at a specific cluster cell, a specific hexagon, which happens to be around Chicago, so our destination for our routing. So this is the time series, so a single portion of our space-time cube for that specific cluster cell. We see here the element numbers that are according to the time intervals. We do see here the start timestamp, and we also see that the individual intervals are 4 hours long. And now for each individual cell in my space-time cube, I have the count of the observation, as well as the count of the ships and some additional percentage logic, which doesn't matter too much as of now. So what we did in this exercise, we kind of prepared our data for time series forecasting. We extended spatial clustering for a time dimension in Z direction by having a single function, which we call for each time slice, and an orchestrating function, which at its heart uses the map merge operator to execute a function per individual time slice. And in the end, we dumped out the data in a table, which now represents our space-time cube. Now, let's do the actual forecast. And for that, we're switching over to the predictive analysis library. Again, this is the function, this is the space-time cube we just created. Let's inspect that space-time cube. So there are over 500,000 cells in there. So again, if we go back to our image here, so our space-time cube consists out of 500,000 of these smaller cubes, of which is made up. Okay, so it's pretty granular, that thing. What we do see here, for example, is that for each hexagon, for each spatial cluster, there are 365 observations, which are 4 hours interval within 2 months of time. And likewise, if we're looking at how many spatial clusters are there for each time slice, we see that each element number, each time slice, here now indicated with a start timestamp, does have 1,500 and something cells, which are the hexagons. So this gives you an idea of the dimension of the cube that we just created. Now we want to run time series forecasting on that data. And for that, I'm generating a view which exposes my space-time cube, which exposes my data. This is a kind of for simplicity reasons, and our code can be reused later on. I'm creating a second table which will contain my results afterwards, essentially the forecast. This is what I do right now. Now, we are calling out to a specific time series forecast algorithm, which is integral part of the HANA database. It's part of the PAL. It's part of the predictive analysis library. And the specific set of algorithms are called exponential smoothing. And there is a unified interface for running exponential smoothing. And in specific, we will be using a variant of it, which is called massive auto exponential smoothing. This is what it is. Massive stands for we're running not a time series forecast on a single time series, we're running it on multiple time series of our space-time cube in parallel. Auto exponential smoothing means it will try to find the best model out of the variants of exponential smoothing, which there is single, double, and triple exponential smoothing in essence. So it will run all of these and then have a certain metric on which it evaluates the model, so to say, and chooses the best model for that specific time series we are looking at. So there is a short do begin end block where we basically set the parameters for our PAL algorithms. So we're using massive outer exponential smoothing, and we want to have 12 intervals to be forecasted. These are the most prominent ones. We are calling PAL unified exponential smoothing, that built-in function. We give it the data, we give it the parameters, and we want to yield the forecast. So let's run that code block again on over 1,500 individual time series. Completes in a couple of seconds. And what you see here, for example, is the result for each individual cluster. So for cluster 1, it chooses single exponential smoothing, I guess that is. And there should be here, for example, for that cluster, the time series in that cluster was best modeled using double exponential smoothing. Now, we can take at the cluster at Chicago, which we are concerned with. So this is essentially the output. What we see before, we had the 365 time slices, time intervals, which were observed data, 2 months divided into 4-hour intervals. And now these are the 12 intervals that have been forecasted along with confidence values here. Now, obviously, what we want to do is plot that data. And for that, I'm joining the output of my time series forecast with the actual data. And I'm jumping over to Database Explorer. This is the view that I just created. And this is the historic data and the forecasted data. I've created a bar chart where I say the x-axis is my timestamp. These are the 4-hour intervals. The blue bars indicate historic observed traffic data, number of ships in this specific cluster cell. And the orange bars indicate the results of my time series forecast. So these are the forecasted values for the next 12 intervals, for the next 12 4-hour blocks. Now, back to our question from routing. If Sturgeon Bay is blocked and I need to take an alternative route, and I can calculate a new estimated time of arrival, which is, let's say, 8 hours later or something like that, I can use the forecast, for example, to understand, instead of meeting about 15 vessels at Chicago port when I arrive, I might end up meeting about 50 vessels which wait there to be unloaded. So this is how we can leverage the time series forecast on our space-time cube in conjunction with routing in order to get an understanding of an impact of closing down Sturgeon Bay. Okay. Let's recap a little bit. So we predicted traffic. For that, we used that space-time cube. Again, just a set of spatially organized time series. We created the space-time cube running that spatiotemporal clustering function, which I showed earlier. And then we used massive outer exponential smoothing. Even for non-data scientists like me, it's a function which I can use because it's very much automated. Massive, because I don't have a single time series which I want to forecast, but actually I have 1,500 time series which I want to forecast. And finally, we've brought the result of that forecast into a bar chart in our Database Explorer. Now, this concludes the first piece of the demo exercises. We will be now switching over to enterprise search. So we will leave the spatial and the graph and the PAL algorithm and go over to how do I find stuff in HANA. Now, enterprise search is more than the contains predicate, more than simple full text search on natural language data. As a matter of fact, enterprise search is quite a huge topic in SAP HANA Cloud because there is modeling. You can create search models and model the search behavior on your data. You will get federation. So you can have multiple search models in your system and search them all at once. So this is like executing all your BI reports in your BI systems all at once. And finally, there is a kind of a starter kit, a development starter kit, which provides SAP UI5 Fiori user interface. If you're interested in that, there is the Enterprise Search Developer Kit, which I just also will be using for the demo here. Here's essentially what it does. This is my HANA system. I will create a search model in HANA, and then I will be using the development kit in TypeScript in order to expose the data, the search queries, and the search results into a search UI. So this is what I will do. First, we will be creating a search model. And I will be searching vessels, vessel names, vessel types. And for that, I have created a few, which does a little bit of projection, and essentially for each vessel gives me its last observed geolocation, its last observed position. I have that logic and that view, and I will dump some data in a table, which I will search on later. The table is called vessels. I will create it, and I will simply now the data generated by my view, along with some textual data into my new table. Let's take a look in a second what that looks like, what our search data looks like. This is what we want to expose for enterprise search. It's vessel data. Again, we have the key MMSI. We have the vessel name here, along with its call sign, its vessel type, if it's a cargo ship or a passenger ship, along with its last observed location and width and cargo characteristics of that vessels, if there are. Now, a little bit of modeling. There are different ways to create search models in SAP HANA. And one way to do it is by using the built-in procedure ESH, Enterprise Search Hub config. And what it takes is that specific JSON syntax for describing search models. So basically what it is, it describes what the source is, where the data resides, which is my view that I've just shown you. Then it gives you some labels. So I can say, okay, the plural label is vessels, and yeah, it should be enterprise search enabled. And now I can define the properties. Essentially, for each individual column, for each individual field, I can tell the enterprise search system how to search in that system, and actually if that field is returned into a search UI, where is it organized? Is it a key? Is it in the first position, or should I calculate a facet? All that is defined in that search model. So for example, the vessel name should be searched because it's a short string, and with a fuzzy option here, and the vessel type, again, cargo versus passenger and the like, that should go into a facet. I'll show what that means in a second. So simply calling the procedure with that payload will generate a search model in my HANA system. Then there is a built-in procedure. This is one way to run enterprise search queries. There is that built-in procedure ESH_search. It takes an OData like query with an OData compatible extension for full text search. So what this does is it runs a query for the string n here in that case. And what it returns is a piece of JSON, which I don't want to explain you, but which is easy to understand and easy to bring into a user interface. So let's go to my user interface. This is the SAP UI5 user interface that is part of that starter kit, which I showed you earlier. And it simply connects to a HANA backend system and reads the metadata for all the models that are in that SAP HANA system. and then it's completely generic. So what we see, I only have a single model for the vessels, which I just created. I can search on my 700 something vessels down here. And what is automatically generated is these facets that allow me to drill down into the result set. But of course, I do want to search for something. I know there's a vessel Beatrix or something like that. So this is a standard result set here. The nice thing is, because I have the last location, I actually can bring the results on a map, and I can understand that the vessel Beatrix, which I search for, is currently here in that position. So that much for enterprise search. There is a lot more to enterprise search. There are different ways to define these models. There are specific syntax how to do the query federation, so essentially run over multiple sets of search models at once. So you can do a cross search within a system. You can even do a federated search across systems. So there is a whole lot to enterprise search. This is just an extension. It's a built-in component in the SAP HANA database, and just like spatial and just like graph and just like predictive, it's there. It can be used on a single copy of the data, and it allows you to power full-text search user interfaces. Okay, quick recap of what we did. We've generated a little bit of data by looking at our vessel data. We have stored that data in a table along with the vessel's last position. And when we have used one option to define a search model, which is the built-in procedure ESH config, it's a defined syntax on how to create these models, how to define the characteristics and the behavior of that model. And when we've run a search query, ESH_search, which takes an OData syntax as a query and returns JSON, which is very handy in order to power user interfaces like the one that is provided by the development kit. Now back or forward to our last exercise. So far, we have been working with flat data, tables, relational data. We've used spatial for that. We have created a vertices and edges table so that the graph engine can operate on a network. And in this exercise, we will be actually working with JSON data, so non-relational data, essentially. In SAP HANA Cloud, there is the JSON document store. Besides the row store and the column store, it's a separate store, yet fully integrated into SAP HANA Cloud, and that store stores JSON. So what's the benefit of storing JSON? So there might be applications that generate JSON anyway. So it might be a good idea to simply store that JSON and give it back because the application looks like that. So there is no need to kind of decompose that JSON into a relational model. Also, I mean, if you're dealing with JSON, you have things like arrays and nested object and things of that nature that is all capable of being represented as JSON. So the JSON document store, this is a single thing that stores JSON. However, as it is an integral part of the SAP HANA database, it actually runs in the same transaction domain like the column store. So what you can do is you can write joins between your relational tables and column store and your JSON documents in the document store. That's one benefit of the document store being integrated or being an alternative, an additional store within SAP HANA Cloud. Now, the data for our last exercise is coming from GDAL, from the GDAL project. They are essentially ingesting an enormous amount of news data, articles, worldwide articles. And they are analyzing that using natural language analysis techniques, but also other techniques. And there is one specific data piece, which is the global event graph. Global entity graph. Where is it? Here is it, the global entity graph. It basically extracts out of the news article all the named entities that are mentioned in there. So things like persons, organizations, locations, events. Those are parsed out of the news articles and that are provided with that global entity graph dataset. There is each 15 minutes or so a new pack. For the news that have just been released in the last 15 minutes, they are analyzed, and then a new data set is published on that GDAL data set. Now, in the case of the global entity graph, the data comes in form of JSON. So what we see here is for at this date, there was a URL, it's some Indian news article that was written in English language, which contained a set of entities. So I've cut it down. So this is the way how the entities are transported. I have a name, I have a type, and there are certain other attributes to the entities that may or may not be present. For example, that Wikipedia URL. So in order to ingest the data, I will be switching over to a Jupyter Notebook. And I will be using HANA-ML. That is the Python client for machine learning in SAP HANA. So primarily, the HANA-ML package was created to have a Python interface so that data scientists can leverage the PAL functions, which are part of HANA, where they can work with the in-database algorithms of HANA. During the last couple of revisions or versions, we extended HANA-ML to be also providing nicer capabilities for handling spatial data and also exposing graph algorithms. And last but not least, being able to handle JSON data, JSON collections. And this is why I'm using a Jupyter Notebook, HANA-ML, the Python API, in order to take JSON data from the GDAL website and put it into a HANA collection. This is the equivalent tables in the JSON document store. So here I've already imported my packages. Here you see HANA-ML. I've connected to my HANA database system. And what I'll do here is I'll pull the results from that GDAL project. It's a specific 15-minute package from that global entity graph. I will do a little bit of data massaging. So I have a real intent, and especially parts of the data is mail formed. So essentially there is invalid JSON on the data, and I'm doing a simple trick to kind of deal with it. So now I have a JSON at hand in Python, and now I will be using the HANA-ML function, create collection from elements. So it will take the JSON that I have in Python, and it will ingest it into a HANA collection. Of course, this is not the only way how you can ingest JSON data into HANA, but I thought I should bring in Jupyter Notebooks. So bear with me while the data is now replicated to my collection called GDAL_GEG. Switching back to DTBeaver and inspecting the collection that I have just created. A collection in JSON document store looks like a table with a single column. There is that JSON document in there. And we are also using SQL in order to query the JSON document store. So actually select star, brings back the actual document. Here we do see that one specific document, you see the array of entities, there's a person, there is something other, there's a lot of other, there's an event in there, in that news article. Now, what we want to do in JSON document store, we want to unnest that entities array. And for that, I'm using the unnest function of the JSON document store. And I will be unnesting these entities. So out of that JSON array, I will creating single records, so to say, and bring that back in a table-like structure. This is how it looks like. So these are now all the entities mentioned into that in that specific article. It's written in English, and we find things like CEO and company in there. Yeah. And here in that news article, for example, there are two locations mentioned, Poland and Ghana. And since they are very common entities, they kind of have that identifier, which refers to a specific DBpedia URL, I guess, something like that. It's a kind of an identifier. So we can, across languages, identify these named entities. So no matter if Poland was written in English language or in German, which is Poland, or in Russia, which I cannot pronounce, it refers to the same entity. And what we will be doing next is we will, first of all, put a view on top of our entities so we can filter for the entity types that are of interest, pole entities, which we are interested in. So let's take a look at that. Nothing surprising here. Again, we're just restricting to persons, organizations, locations, events. So this is a little bit duplicate. Forget about that. But what we see here is that the global entity graph from GDALT harvest the results from news article being written in multiple languages. So most of them are in English, but there's also Russian, Chinese, and German in there, of course. What we want to do is we want to create a graph out of that. And the logic behind that is within an article, if two entities are mentioned together, we simply pull an edge between these entities. So we are kind of creating a co-occurrence graph, but only for entities which are kind of salient in that article, so which are prominent in that article. And for that, I'm creating a view which exposes the edges. It does a little bit of that ID generation here, but it essentially joins the entities to itself based on the URL. So the entities need to be named in the very same URL news article. And what that gives me is our co-occurrences. So looking at the data provided, we do see that Mexico is a location, and it's mentioned along with US, which obviously is also a location, in 6 different articles and with a high salience. Let's see if we find something else which makes sense. There's a person named Jill Biden, and she's mentioned together with Vivek Murthy, which I don't know, I have to admit, together in the news article. So you get the idea. We are generating a co-occurrence graph. Again, like before, for simplicity reasons, I will be generating an edges table to store that data. I will use the view, which I've just shown you, in order to fill the data from the JSON document store into my relational table. And I will create some vertices, some nodes out of that. I will simply take all the entities mentioned as source or target in the edges. So, a little bit of overhead here, but again, just like before, we can create a graph workspace, simply pointing to our entity edges, co-occurrences, and our vertices table. So let's do that for a second. And now we could utilize the HANA Graph Engine to do something meaningful with it. Well, what I would like to show you is a preview of a plugin or an adapter to Cytoscape. Cytoscape is a rich client which is used for graph analysis, network analysis, most probably in life sciences and healthcare. Very mature, very capable. A lot of layouting and styling rules can be applied here. And the reason I'm bringing up here is that my colleague Matthias Kiemeter wrote a preview, which is available out there on GitHub, of a plugin. And the plugin allows you to connect to a HANA database, which I need to do here. And it allows you to load a graph from a workspace. So this inspects the HANA system, and then I can inspect my global entity graph, which I just created. And this is what it looks like. These are now pole entities. So let me figure that out. New Zealand, so the lilac thing is obviously a location. The green thingies are obviously events. So there's a World Cup happening here. The yellow things seem to be persons. There is Shardul Thakur. And the orange thing actually should be something like organizations. That's what I was missing. So what we're seeing here is a way to explore the kind of entity core currents graph, which we generated via Json, and which we layouted here in Cytoscape in order to understand what has happened in the last 15 minutes or in the data contained in that package. So we see a lot of persons being related. Let me see if I find something cross-lingual. I'm pretty sure there is some Russian in there. I don't find it right now, but there is some data from Germany. Aldi is a supermarket, it's a store, stuff like that, and you can try to understand what's going on in the world, what is talked about, and which things do relate to each other. Again, the plugin is currently a preview. If you want to download it and use it with Cytoscape, the link is actually within that GitHub repository. So let's summarize. We use the JSON document store in order to ingest JSON data from the GDAL project representing named entities found in news articles. We've ingested the data using HANA-ML. There were other ways, but I wanted to show HANA-ML and that create collection from elements function, which is part of the HANA-ML library, which checks JSON and pushes it out to SAP HANA Cloud JSON collection. Then we've done some co-occurrence magic in order to generate edges, relationships between entities being mentioned. And finally, we've ingested the graph workspace into Cytoscape for further analysis. Again, here's Matthias' blog on how to explore networks using Cytoscape. So that concludes the workshop. Again, what I want to point out, if you want to run through these exercises on your own, you can do so. Data and code is there in that GitHub repository. If you happen to have just a HANA Cloud trial instance, you cannot do the exercises with the PAL and you cannot do the exercises with the document store, but you will recognize. Especially the logic around motion statistics, dwell locations, the space-time cube is created in a way that you can reuse it. You can grab the code from there and easily adapt it to your data. And again, if you have space-time observation, so geolocation with a timestamp and an identifier of that thing, being it a runner in a Strava application, be it a suspect in a police investigation, or an airplane, or your truck carrying your goods from A to B. Whenever you have these space and time observations, you basically have an identifier, a location, a geolocation, and a timestamp. And that is the basic data on which you can make all that logic running. This is all that is required to identify motion statistics, dwell locations, do spatiotemporal clustering. So Again, if you want to do it, go to that repository. If you require some additional background material, you will find it in that second page here. There's a link to the spatial resources. It's essentially currently organized by Matthias Kemeter as a long linked list with the most prominent, most valuable resources in the spatial area. And there is also the same for graph and machine learning. With that, I would say thanks for your time and thanks for watching. If you have questions, of course, you may reach out to me or via the GitHub repository using the issues functionality there. Okay. Then, as this is a live session, no live Q&A. Again, thanks for watching. Try out the stuff. Look at the repository, get yourself educated, and otherwise, please evaluate the session. There should be a link on where you can rate the session and provide feedback. And otherwise, I wish you a great rest of TechEd.